Hello everybody, welcome to part 4, and now we're going to finish up by looking at the chemical or the non-clastic sedimentary rocks. Oh, went a bit too far there, sorry about that. So in terms of the chemical sedimentary rocks, we are looking at precipitation of material which has occurred by either inorganic processes, so something like evaporation, or by organic processes, so a biochemical origin, so something like coral or an oyster making its shell larger. You can see that in both of these instances we're not dealing with a situation like the clastic sediments where we have pieces of sediment being transported around. Most of these processes are going to take place in the same location as the sediment will be deposited. So what are our types of chemical sedimentary rock? Well, we have limestones, we have chalk, we have dollarstones, rock salt, gypsum, chert, coal and iron formations, to name but a few. There's a whole range of them, but these are by far and away the most common ones. And you can see that next to them I've noted whether they are organic or inorganic. So in terms of rocks formed by organisms, you can see in both of these instances we have a situation where we have shelly material like coral and bits of shell and crinoid being incorporated to make sedimentary rocks. And in this instance we have a situation where we have undecomposed plant matter being used to make coal, in this case another chemical sedimentary rock. So let's start off with the most common of all the chemical sedimentary rocks, and that's limestone. Now limestone has several different subgroups, and we're going to have a very quick look at some of them now. So limestone is the most common of the chemical sedimentary rocks, and it can be organic or inorganic in origin. There's a few ways in which we can make the calcium carbonate. So it's composed chiefly of the mineral calcite, and calcite has the chemical formula calcium carbonate, CaCO3. Now, if it's organic, the calcium carbonate will typically have come from pieces of shell. Obviously, the shell it will be of organic origin because it was made by an organism. In the case of chalk, the calcium carbonate will have come from little microscopic organisms. And in the case of something called micrite, it can come from microscopic organisms as well. Now, in terms of inorganic ways of getting calcium carbonate, we can get it through the evaporation of seawater. We can get it through calcium carbonate precipitating directly from seawater onto something. And we can also get it, once again, in the form of micrite, which is sometimes called carbonate mud, which, as you just saw, can also be formed by organic processes. So, little bit more explanation might be helpful. So, organic limestones are produced from shelly material, and this can be from animals that actively precipitate carbonate onto their bodies, so something like an oyster making a shell, or it can be from animals that have passively precipitated carbonate onto their bodies. So, little single-celled blue-green algae happily floating around in seawater in the right area can actually have calcium carbonate precipitate onto their bodies even if they don't want it there. So another situation is oolitic limestones, and these are made up of things called ooids, and they're little millimeter scale balls of calcium carbonate, and the carbonates are precipitate from seawater onto a piece of detritus. It could be a little bit of quartz or a little bit of shell. The calcium carbonate comes out of the seawater and precipitates onto that nucleus. Now, the reason that the calcium carbonate precipitates onto the nucleus is a little bit uncertain. It could just be calcium carbonate coming straight from the seawater, or it could be calcium carbonate precipitating onto the nucleus because there's a very thin layer of algae on the nucleus, and that's encouraging the calcium carbonate to come out of the seawater and form on the nucleus. So we're not 100% sure about the mechanism. All we know is that in the end you end up with these small millimeter scale calcium carbonate balls which look a little bit like jawbreakers when you cut them in half. So what's micrite? Well, micrite is commonly called carbonate mud, and you can see here's a very nice picture of it right here. This is from the Florida Keys. So you can see this material is extremely fine grained. It's just like mud, clay and silt-sized particles, the kind of stuff that's carried by rivers. So micrite stands for microcrystalline calcite. It will only form in low energy environments like lagoons. As you can see, it's very, very fine, and an ocean is quite a high energy environment. So very, very fine material like this, if it's left exposed to the ocean, will simply be dissipated by waves and it will be lost. So if we are going to form micrite, it means that we have to form it in some kind of protected environment. I do apologise for my dog, it's barking at somebody outside, I don't know who. Now, how do we form micrite? Well, there are lots of ways in which we can form micrite actually. So the most common way of forming micrite is through a mechanical erosion process of larger particles. So the first way we can do it is if we have some kind of organism that is eating something that contains carbonate. As they eat the organism, calcium carbonate will go into their body, but they can't do anything with the calcium carbonate, so they'll just simply poop it out the other end. Another method by which we can form these very, very fine carbonate particles is if we have a beach that's covered in shells. Every time a wave comes onto the beach, it causes these pieces of shells to bang into each other, and it knocks off these very, very fine pieces of calcium carbonate, and that can become micrite. We can also get micrite when the calcium carbonate precipitates onto algae and plants. So if we look down here, here's a plant from a carbonate lagoon, and you can see it has this white powdery material on it. And all that is calcium carbonate coming straight out of the seawater and precipitating onto the leaves of the plant. When the plant dies, obviously the organic material will decompose and be lost, but these very, very fine calcium carbonate crystals will simply be incorporated into the microcrystalline calcite, the micrite. And the final thing we can do is we can have the micrite simply being precipitated directly from seawater. So we have calcium carbonate in that seawater, and some of that calcium carbonate decides to precipitate out of the seawater as calcium carbonate crystals that simply rain out onto the bottom of the lagoon. So there are organic methods, there are inorganic methods, and there's just a mixture somewhere in between. So micrite can be formed from a range of different processes. Essentially, the moral of the story is in the end what you end up with is huge quantities of very, very fine-grained calcium carbonate. Now, micrite is very, very important because it is one of the primary forms of calcium carbonate that goes to form limestones. So if you want an example of a micrite generating system, we need to look no further than the Florida Keys. So you can see it right here. Here's our lagoon. Here's the barrier island coming along the front there, protecting the lagoon. And if you look at the lagoon, it has this very distinct creamy white colour to it. That is all of this carbonate mud in the water. It's giving that water that very creamy appearance. And so what's going to happen is over time this lagoon back here is going to steadily fill up with more and more and more carbonate mud, and eventually the lagoon is going to become completely filled by it, and eventually it will become liquefied to form a limestone. Now, in terms of the ooids, these little particles I was talking about, these are what ooids look like when you look at them in real life, and this is what they look like when you look at them down a microscope. So right in the center here, there's going to be some kind of particle, and that's going to be the nucleus around which the calcium carbonate has been deposited. And so what happens is ooids will tend to form near the beach, where the water's being stirred up by the waves, and the ooids will be rolled by the waves one way, and they'll be rolled by the waves the other way, rolled backwards, forwards, backwards. And that means over time you manage to build up these nice, even, concentric layers of calcium carbonate around the nucleus. Now, as I've just discussed, why the calcium carbonate deposits itself on the nucleus is uncertain. It could just be calcium carbonate coming straight from the water and it precipitates itself onto the nucleus. That's one reason. Or it could be there's a very, very thin layer of algae on the nucleus, and the presence of the algae encourages the calcium carbonate to come out of the seawater and form these layers. We're not 100% sure. So, I should go back for just a second actually. So if we have enough of these ooids, they can actually combine themselves together to form a type of limestone which we call a oolitic limestone. It's made up of nothing but these ooids. Now, if we have a limestone that consists of nothing but pieces of broken up shell, typically formed in a beach environment, that type of limestone is referred to as a coquina. If we have a limestone that typically forms from nothing but micrite, it's often referred to as a macritic limestone. Now don't worry, you're going to see these different types of limestones when we look at them as part of the lab, so we're going to get a better look at them in the relatively near future. So what other types of rocks are formed by organisms? Well, the obvious one is chalk. So chalk is technically a type of limestone. It's calcium carbonate. And chalk, though, is formed by the accumulation of microscopic organisms, very, very small animals that float around freely in the ocean. So that's what chalk looks like. And we're very familiar with chalk. It has that very powdery, dry feel to it. So chalk, when you actually look at it, is a pretty unremarkable looking rock. There's nothing very special going on there. However, this is what chalk actually looks like when you look at it down a very high power microscope. So you can see that each of these is a shell, or a casing from one of these very, very small microscopic organisms that was just floating around in the ocean water, happily photosynthesizing, doing its thing. And over time, the shells of these organisms built up and up and up and up until the layer that they produced was so thick that it could be lithified to actually form a rock, and that rock is referred to as chalk. So what about coal? Well, coal is composed of organic material, so we're thinking about plants, and coal will form in swampy environments. Now, the most important thing is the organic material must be deposited into an organic environment which is wet and low in oxygen. So we're looking at a swamp. It has to be a swamp pretty much, or a lagoon. So why is it low in oxygen? Well, if you've ever been to a swamp, think the swamps of Louisiana for instance, you will know that those environments are very, very heavily vegetated. Lots of plants. So that means every day there's plants dying, falling into the water and floating to the bottom of the swamp. Now, when those plants go into the water, they begin to decompose, and the decomposers, the animals that actually break down the plants in the water, do that work. They begin to break down the organic material, but there's a problem. In order to break down the organic material, they need to use oxygen. And so as they decompose the organic material, they begin to use up the oxygen in the water. The problem is the water in these lagoons and these swamps, it doesn't really get agitated. So it's very difficult to get new oxygen into the water. So the decomposers use up the oxygen, but it's very difficult to get new oxygen in. And so what happens is the water in these lagoons and these swamps becomes anoxic, or oxygen poor. So what that means is when a piece of plant material, a tree for instance, or just simply some leaves, fall into the swamp water and they sink down to the bottom of the swamp, they don't decompose because the decomposers have all been killed because there's no oxygen there for them to survive. And so what this means is you have a swampy environment and you end up building up a layer of plant material in your swamp. Now, this plant material, if it's very lightly compacted, forms a layer of what we refer to as peat. So peat is the first stage in coal formation. It's very, very low grade coal. Over time, as more and more material builds up over this layer of organic material, and the layer begins to be compressed a little and heated. Now, when it gets heated, it starts to drive off the impurities. So as your layer of organic material gets heated, it starts to drive off the water and the sulfur and the phosphate compounds and the nitrogen compounds. So the more we heat up our layer of coal, the more impurities we drive off, and that's good, because we want high quality coal with very few impurities. So as we begin to heat up our coal, the next layer, next type of coal we get is something called lignite. And lignite is still pretty rubbish coal, to be honest. When you burn it, it's very, very smoky. Now lignite, on the other hand, when you compact it even more and heat it up even more, you eventually end up with something which is called bituminous coal. And bituminous coal is referred to it because it contains something which is referred to as bitumen, also sometimes referred to as asphalt. That sticky stuff we use to essentially cover the surfaces of roads in some occasions. And bituminous coal, if you actually hold it, has a rather distinctly kind of hydrocarbon-rich smell to it. A little bit like gasoline, but not quite as strong. And that's the bitumen within the sample. Now, if you keep heating up your bituminous coal even further, you drive off more and more of the impurities, and you end up with the highest quality of coal, which is something called anthracite. And anthracite is the type of coal that you really, really want to burn if you are going to burn coal. But the problem is it's not that common and it's quite hard, so it's difficult to mine, so it's rather expensive. So that means that the anthracite mines of Pennsylvania, very, very good quality coal, unfortunately can get undercut by coal from countries like Germany, which is mostly lignite, very, very poor quality, but much, much cheaper. And so unfortunately, it makes it very difficult to mine good quality coal. So most of the stuff being burned in power stations is relatively low quality coal, hence the fact we end up with a lot more pollution from coal burning power stations than we really need to. Now, if we take this even further and we heat the anthracite, we take the anthracite under even higher pressures and temperatures, eventually we'll end up driving off all the impurities and we'll be left with nothing but pure carbon, at which point we have graphite. So essentially coal has several stages, and each of these stages is the result of increasing pressure and temperature as our layer of organic material gets buried deeper and deeper and deeper. So it goes peat, lignite, bituminous coal, anthracite, and finally the highest version would be graphite. So this is an example of an environment where we are currently forming coal. So this is the Everglades National Park in Florida, and you can see that the water here is very murky and very dark, and that's a reflection of the quantity of organic material that's fallen into the water here but isn't decomposing. Undecomposed organic material tends to have quite a dark brown to black colour to it, and that's helping to give the Everglades here this very, very distinct colour when you look at it in a satellite image. So what about rocks which are formed due to evaporation? So very common rocks that are formed through evaporation are rock salt and gypsum. So in order to form these rocks, you just need to have a large body of water, and that body of water needs to evaporate away. And there's only a few controls. The most important thing is your body of water has to be in a hot environment. So you need to be in a desert or semi-desert environment. And your body of water needs to have less water coming in than is being lost to evaporation. So you need a net loss to evaporation. So that means every day you're losing more water than is being put in from whatever the source is. And so that means over time, the water evaporates away, evaporates away, evaporates away. And as we discussed right at the start, as the water evaporates away, it can't take the minerals dissolved in it with it as it evaporates and goes into the atmosphere. It has to leave them behind. And so what happens is over time, your water becomes more and more concentrated in these dissolved minerals, and eventually it gets to the point where the water is just so full of these minerals that it will just start to precipitate them out. Now, if you go to the extreme and the water completely evaporates away, as the water goes, it will just dump all the minerals as it's evaporating away. So that would give us something like this picture here. This is the picture of the salt flats outside Salt Lake City. And Salt Lake City, the salt flats were produced by a very, very large lake that formed during the last ice age. During the last ice age, the area around Salt Lake City was actually quite nice. It would have been temperate, a little bit on the warm side. You could call it maybe ever so slightly tropical, just ever so slightly tropical. And what happened was, when the last ice age finished, the glaciers retreated north towards the North Pole, and unfortunately that meant that the temperate environment around Salt Lake City was replaced by the drier, more desert-like environment that it has now. And so what happened to that massive lake? Well, of course, it began to evaporate away, and as it evaporated away, it left behind all the dissolved minerals that were in the water, because obviously the water, as it went into the atmosphere, could not take those minerals with it. So evaporites will typically be dominated by a couple of different types of rock. The first type is rock salt. As the name suggests, it's made of salt, or halite, as geologists prefer to call it. And the other version, oh, there's my dog again, and the other version is gypsum, that's calcium sulfate. Both of those are very, very common evaporite minerals. I'm not going to worry about travertine right now, I'm going to be honest, because I'm not really going to discuss it with you guys. Another type of sedimentary rock that does make an appearance sometimes is chert. So you may have heard the term chert and the term flint. So in the old days, chert and flint are the same thing. It's just silica, SiO2. Very, very, very fine-grained pieces of quartz. Very, very small crystals. You can barely see them with a microscope. The initial classification was, if it was light in colour, you called it chert. If it was dark in colour, you called it flint. And that way of splitting them up was completely pointless, because it depended on the view of the person doing the splitting up. If they thought that bit looked light, they called it chert. If they thought that bit looked dark, they would call it flint. It was a pretty useless system. So now what we've done is we've decided that flint is a completely silly term, and it's just all chert. The term flint is still used. It's typically used by archaeologists when they're describing arrowheads and other tools made of chert. So they'll typically use flint to describe that type of material that's been worked by early humans to make tools. But in terms of geology, we refer to it now exclusively as chert. So as you can see from the picture here, this is a pretty standard setup for chert. The chert itself, you can see, comes in the form of these large nodules, and they're typically linked together by these thinner tendrils in between. Now there's a couple of ways we can form chert. Both of them are a little bit complicated, so we're not going to go into them in huge detail. The first way we can form chert is when we have something called a siliceous ooze. And the siliceous ooze is a very deep marine sediment, so it's very, very, very deep seawater. And the sediment itself contains lots and lots and lots of microfossil skeletons, which are made of silica. So if I go back for a second, these are the microfossil skeletons, the microfossil shells. Imagine that instead of being made of calcium carbonate, they were made of silica, SiO2. And so imagine you built up a whole load of those, and they ended up forming this layer of what we refer to as a siliceous ooze. Well, if you liquefy that in the correct way, you petrify it, that siliceous ooze can turn into chert, a layer of chert. The other way we can form chert is if we have a groundwater, a water moving underground, which contains silica dissolved in it. And what will happen is as that groundwater moves through a layer of rock, typically a limestone or a chalk, the water, which contains the silica, will react with the rock. There will be a chemical reaction, and that chemical reaction will cause the chert to be precipitated by the groundwater. And this is what you can see in this picture here. You can see all of these, all these veins here. They represent where water has been moving through this limestone. And as the water's been moving through the limestone, it's been depositing excuse me, it's been depositing the silica as it goes, which eventually forms the chert. A couple of other rocks. Dolostone. So dolostone is not a primary rock. It's made of a mineral called dolomite, and dolomite is calcium magnesium carbonate. So calcite, the stuff that makes limestone, is calcium carbonate. Dolomite and dolostones, which is the rock that forms from dolomite, is made from calcium magnesium carbonate. So the most common way of forming dolomite is during the lithification process of a limestone made of calcium carbonate. It comes in contact with a fluid which contains magnesium. The fluid containing magnesium reacts with the calcium carbonate to produce dolomite, and that's really the difference. The most important thing about dolomite is it pretty much shares most of the same physical properties as calcite. However, it will not react with acid. When you put hydrochloric acid on calcite, it will react vigorously. You'll see it bubbling. When you put hydrochloric acid, room temperature hydrochloric acid, on dolomite, it will not react. There will be no bubbling. If you want to make dolomite react with the acid has to be hot. You have to heat it up beforehand. The other type of sedimentary rock, chemical sedimentary rock we're going to touch on here, are the evaporites. We've already touched on them, gypsum and halite. They're formed when you have large bodies of water evaporating away. We're not going to go into them in great detail. If you really want to know more about these kind of processes, historical geology covers a lot of this kind of stuff happening during the history of the United States. So, in terms of evaporites, as discussed, evaporites are formed when bodies of water evaporate away. It can't take the dissolved minerals with it. And a classic example of that is inside a kettle. So here's the interior of a kettle, and you can see it's covered in limescale. Okay, if you have ever gone and drained a water heater in the attic of your house, you will also be very, very familiar with limescale. So limescale is just calcium carbonate, and it's dissolved in the water. But as you boil the kettle and the water evaporates away, you will have seen it as steam coming out of the kettle. It can't take the calcium carbonate with it, so it leaves it behind, and over time it begins to form a rather substantial layer, like you can see in this picture. So halite is exactly the same situation, and gypsum as well. We have a body of water evaporating away, and it leaves these minerals behind because it can't take them with the water that's evaporating into the atmosphere. As discussed, in order to form evaporites, we need what's referred to as a restricted body of water, like a lake or a small sea, in an arid climate where it's dry, and you need less water coming in than is being lost to evaporation, so you have a net loss to evaporation. So a good example of this process is the Mediterranean. So underneath the Mediterranean Sea, so between Europe and Africa, there is a 2-kilometre thick layer of evaporites. And so what happened was, about 7 million years ago, the Mediterranean Sea got cut off from the Atlantic. And so that meant that the only water going into the Mediterranean was coming from the Nile and the Danube and a few other rivers. And unfortunately, that's not enough water, because as you also might know, the area around the Mediterranean is very hot and very dry. So it has a very, very high rate of evaporation, and there wasn't much water coming in. And that eventually led to the Mediterranean more or less completely evaporating away and leaving behind these large evaporite deposits. So gypsum halite is a mixture of the two, is here in yellow. Gypsum and halite green, and only gypsum in pink. So you can see these huge quantities of evaporites left behind by this evaporation event about 7 million years ago. And you can actually see the evaporites if you look at this. This is called a seismic section. It allows you to look through the layers of rock under the surface. And so all of these layers of rock are just standard sediments that you would expect to get in a small sea like the Mediterranean. But this portion here, from there to there, is about 2 kilometers thick, and that's the evaporites left behind by this event about 7 million years ago. So a really good modern example of this event is the Dead Sea. So the Dead Sea, as you know, of course, separates Israel and Palestine over here from Jordan over here. And as you can see, the Dead Sea itself, the River Jordan drains into it, but the flow from the River Jordan has been constricted over time due to dam building, and so that's meant that the amount of water going into the Dead Sea has been substantially reduced. It's obviously in a very arid climate, and so they have a net loss. So this is our restricted body of water here. You have a relatively small amount of water coming in, large amounts of water being lost because the climate is arid, and so we have a net loss, and so this body of water is slowly evaporating away. What this has meant is that the water itself has become extremely dense because it's got a very, very high salinity. So all the previous water that's evaporated away and couldn't take the minerals with it, those minerals had to be dumped on the water that was left behind, and so that water has become extremely salty. And it also means that that water is extremely dense. So if you've ever been to the Dead Sea and you've lied in it, what you'll find out very quickly is you don't have to try in any way to support yourself. You will literally just float in the water with zero effort. Now, this picture down here, is what you can see these are modern evaporites being deposited along the banks of the Dead Sea. And you can see as the water is slowly evaporating away, it's leaving behind these halite and gypsum crystals as it goes, and eventually the lake itself will completely evaporate away. And this link here will take you to a YouTube video that shows you a couple of chaps who are testing to see just how dense the water of the Dead Sea is, and they're doing it using a bowling ball. It's quite impressive, actually. So our final type of sedimentary rock that we're going to look at is going to be called an iron formation. And iron formations have a rather distinctive look to them. You can see you have these repeating bands of these grey iron oxide minerals and these red jaspers, otherwise known as cherts. These are very, very iron-rich cherts. So you have a layer of iron oxide minerals, layer of chert, iron oxide minerals, chert, repeating again and again and again and again. Now, how did iron formations form? Well, iron formations formed due to the precipitation of iron from seawater. Okay, big slide of text, but there's a diagram coming in a second that's going to hopefully make everything a bit clearer. So the Earth's very early atmosphere was oxygen poor. In fact, there was practically no oxygen in it whatsoever. And that's because there were no photosynthesizing organisms. There were no plants. And so that meant there was no oxygen going into the atmosphere. And so the atmosphere was, as I said, oxygen poor. Now this meant that if we had any iron going into the oceans, it would not be oxidized. If iron goes into the oceans now, it becomes oxidized and it becomes iron 3+. We're very, very familiar with iron 3+ because we see it as rust. However, because there's no oxygen, the iron that goes into the oceans from the land and from hydrothermal vents in the oceans never becomes oxidized. So that meant that during the Earth's very early history, the oceans became extremely enriched in iron. There were huge quantities of iron dissolved in the seawater. So what happens? Well, about 3.5 billion years ago, we start getting the first blue-green algae appearing, and they start photosynthesizing, but they can't really do very much. However, about 2.4 billion years ago, the amount of blue-green algae explodes. Loads of them everywhere all of a sudden, and those blue-green algae are photosynthesizing like mad, producing huge quantities of oxygen. All of a sudden we begin to see in the geologic record, we see oxygen begin to increase in the geologic record, or which we see as rocks. So at this point, about 2.4 billion years ago, these blue-green algae are starting to produce so much oxygen that the oxygen they produce is beginning to oxidize the iron dissolved in the seawater, and it's taking it from the iron 2+ to the iron 3+. And so when we have iron 3+ plus oxygen, it forms an iron oxide mineral, like these ones right here. And so the oxygen and the iron came together, they formed an iron oxide mineral, and that iron oxide mineral would rain out onto the seafloor, where it would form a layer. And so that's where these banded iron formations are coming from. They're just due to algae producing very, very large quantities of oxygen. Now, obviously, one of the questions is, why do we have these rhythmic layers? Why do we have these layers of chert, iron oxide, chert, iron oxide, chert, iron oxide? And it's quite a good question. There's been some suggestion that maybe they're seasonal. Maybe the layers that have the iron oxide minerals represent spring and summer. The weather is good, temperatures are higher, so that means the numbers of blue-green algae are much, much higher. And so that means more oxygen, and so that means a lot more iron oxide minerals being produced. Maybe the chert layers represent fall and winter, Where the weather's a bit harder, the amount of blue-green algae are lower, and so there's less oxygen being produced. So there are fewer iron oxide minerals forming, and so that means that you end up with a layer that's dominated by sediments, and those sediments will get turned into chert later. Another option is that it might be some kind of feedback mechanism. So you have these blue-green algae, they're super happy, they are churning out more and more and more and more oxygen. They're really, really good, everything is great, but the problem is they end up using up too much carbon dioxide. But they need the carbon dioxide to live. And so once they exhaust too much of the carbon dioxide, they die en masse. And so during the good times, when their numbers are increasing, they're producing these layers of iron oxide minerals. However, when the carbon dioxide level has been exhausted or at least depleted, all of a sudden there's this huge dying off. The amount of iron oxide minerals plummets, and so that's when we get this chert layer forming. And then we need to wait for the carbon dioxide levels to build back up again, and then the blue-green algae will start increasing in number all over again, and they'll do that again and again and again. It's called a feedback mechanism. So the reason why these cyclical bands occur is uncertain. We're not really sure. So this is the kind of basic situation. So what we have is, here's our ocean in blue, and this represents a hydrothermal vent on the seafloor. It's where very, very hot water from underground comes out onto the surface on the seafloor. Now this hot water that comes out is very, very iron rich. Just to show you how iron rich it is, here's a picture of one of these hydrothermal vents. This is from the Mid-Atlantic Ridge in the Atlantic, and you can see this black water being pumped out by it, full of iron. And so all of this iron is going into the seawater. Now, in a modern environment, it gets oxidized, it gets turned into rust, iron oxide. However, during these very early years of Earth's history, there's no oxygen in the seawater, so the iron in this water just dissolves into the seawater, and over time the seawater gets more and more iron rich. At the same time, there's also iron being deposited from the land, because rocks on the land are also being eroded, releasing the iron in the minerals, and that gets washed in by rivers into the oceans, and so over time more and more of this iron builds up in the oceans. Just to give you some idea, by the way, these red dots represent the locations where we have active black smokers, hydrothermal vents on the seafloor. And so you can see they are extremely common now. They would have been way more common in Earth's early history. So this is a relatively low number compared to the Earth's past. So there would have been thousands of these things pumping out huge quantities of iron-rich water into the oceans. So that's how the oceans became so iron-rich. And then eventually all that happened is we end up forming a layer of layer of photosynthesizing blue-green algae up here towards the top of the ocean. This iron-rich water rises up, meets the oxygen-rich layer here. The iron and the oxygen react to produce iron oxide minerals that rain out onto the seafloor. Done. Simple, not much to think about. So the formation of banded iron formations began 2.4 billion years ago, and it ended 1.8 billion years ago. So we don't make them anymore. And the reason is around 1.8 billion years ago, all the iron in the oceans had been exhausted. And so that's it. Once it was exhausted, you couldn't form these iron layers anymore, and so banded iron formation stopped. Okay, so these are the rocks that we've discussed, and these are the rocks that we'll take a look at during the lab. Alright, that's it, ladies and gentlemen. So thank you, and keep an eye out for the lab presentation.